So my co-founder Arnold is here as well, so you can attack him with questions too. And actually, this is probably the first chat that I've given in about 4 years, given we know why, obviously. But probably the last one was actually here as well, talking about Scala. So we've moved from Scala and we're on Rust now. So there's a story there as well. We were commissioned about a year and a half ago to build a EV, electric vehicle charging system from scratch for a UK client. And we've written it entirely in Rust, every piece. We've written the firmware, we've written the controller software on an internet gateway, we've built an internet gateway ourselves, and it's all in Rust. There is, even the front end in HTML, we're using WASM and U and so forth, right? So we have one hammer and, we bang this Rust nail. And it's not because we don't like other languages or anything like that, but we do have some performance requirements, particularly around energy efficiency and heat generation, which have made us decide to go in this direction. So how do we get through the anatomy of a Rust EV charging system in 10 minutes? And so what I thought I'd do is, I probably should have created a diagram for this. I do apologize, but I slapped this together yesterday. So I wanted to introduce what the main actors are, if you like, in the system. And then I want to sort of drill into each one and just talk about its dependencies, because I think that's what we would be interested in here. I mean, we can talk about EV chargers until the cows come home, but fundamentally you guys are here about Rust, and so let's talk about that. So first of all is the electric vehicle charger itself, what we call the EVSE, and that's the thing that the car plugs into itself, right? So we've built that. The firmware on board there has firmware and software. It monitors the temperature of the case, the heat, the contactor heats. They get quite hot when you start delivering 32 amps through for about 15 minutes or whatever. Current flow, voltage, metering, we meter on board there. Quite a sophisticated bit of software. And people out there say that EV chargers are quite simple inside. They're really not. Actually, there's a lot. They're not just like a plug. They're doing a lot more than just a plug. Then we have what we call a mains board monitoring device. So the EV chargers, plural, we can have many in our network. They obviously are located near the car space, but then the monitor board sits in the switchboard, in the main switchboard, and that monitors things in there, such as mains load, PV output, and so forth, right? Those kind of things. We have an internet gateway that also lives in that main switchboard, and that manages connectivity with the internet. Being a gateway, that's the sort of gateway it is, and it also manages this RS485 network that we have that connects all these devices that we're talking about. People might not be familiar with RS485. It's been around for donkey's years. It's a two-wire system, two-wire network. They're very economic. They can run long distances. You can actually have several hundred meters between nodes, right? And so that means fundamentally that we can put the gateway in a place where there's good network connectivity to the outside world. And it treats that opportunistically as well. It doesn't require it, but we can. The EV chargers can be down in car parks underground with not great networks. Okay, so that's why we can put the gateway somewhere else. We talked about RS485 a little bit. Really is ancient but fabulous. And then we have a cloud service for managing and observing the system. We have actually a very small presence in the cloud. All we're doing there is proxying the outside world coming in, and we hook it up, we tie it up with a VPN, and the VPN is established by the gateway itself, right? It always reaches out. That means that everything lives at the edge, the user interface, the applications, everything, right? And we secure everything at the edge there. So they are the major sort of players in all of this. Inside the EVSE comprises firmware and software. As I said, we're Rust all the way. We are, I would say, reasonably heavily involved in the Rust embedded community. We have gone 100% async by using the Embassy project. So we've been contributors to Embassy as well. And it's a really great reason to go async in embedded in particular. And that is, while you're doing something, while you're waiting on something like the UI, you can be doing something else. And it's actually very important. We're not taking we've only got a single core, right? So it's not taking advantage of multiple cores or anything like that. We are running in a single thread of execution. But it means that we can context switch between other things and get a lot done in a short space of time while everything's nicely started. And then we can go back to an idle CPU state very quickly as well. Firmware and software, as I say, is quite sophisticated. It's 140K in size, right? So that's the sort of target sizes that we can achieve with Rust. We use encryption over 485, and we also support a USB serial interface on there as well. And we were talking about security. There you are, Adrian. We're talking about security. I got a grilling on security earlier. And we've got all the right stuff in there. We do software firmware verifications using ED25519. The software side of things is no standard. It's not necessarily for embedded, but we can use it there. We write signal processors, state machines, and so forth. And we also do all of the hardware design as well. Oh, and I should just mention, that's obviously that's actually our board there, that sort of lives there. So hopefully this is the interesting slide for you guys. Various Rust crypto libraries are used. We've introduced something called event-driven finite state machines. They're actually defined on Wikipedia. I've written some blogs about this over the years as well. And so we use those. Pretty much anything you do in embedded ends up being a finite state machine. And we have a particular variant of that takes commands and emits events, and those events then are applied to state, yielding a new state. And this is a bit of a DSL using macros to actually achieve that. Embassy, I mentioned before, we've contributed the implementation of channels to Embassy. We've heavily provided the continuous sampling for the ADC firmware update verifications for the bootloader, some UART stuff, and I mean lots of things. Some PWM stuff. We've got our own protocol for RS485. We call flip-flop. It's open sourced, and when you come to RS485, you're looking at a half duplex style scenario where you have a client, that broadcasts to servers, can address servers and so forth, and servers can only reply if addressed. That's principally how it works, and been around for donkey's years, but we have our own. It's encrypted. It supports device discovery, software updates, and a few other things. And then we use Surday and Postcard for serialization. We have this monitor board, pretty much similar to this EV board. So it monitors three-phase current, three-phase voltage, solar current, and we can make decisions based on mains load of the house or the property in terms of, and then we can signal to the EV chargers, don't let this car charge more than X, and so forth. Yeah. And again, sorry, and again, that is the actual board that we've sort of come up. That's being manufactured right now, which is why we don't have a picture of it. We're quite proud of that board, aren't we, Arnold? You like that one? We actually built this one too, this internet gateway. So we built our own internet gateway using this Amiga 2S chip. It's a MIPS 32 chip. That's 128 meg of RAM. I've got it all written down here. 500 megahertz processor, single core, 32 meg of storage. Right, and so we've sized our application to work within that environment. It works very well. We've customized our own version, our own flavor of OpenWRT. I mean, that's kind of what you do with Linux. You end up customizing at some point. Not the business I really want to be in, to be honest. I don't want to become a Linux expert, kernel expert, but we kind of had to become sufficiently so. Then we have our software and our client software that runs on there, and there's back-end and front-end components to that. But we're now talking, because it's OpenWRT and it's Linux, we're back in the standard world. So before, with firmware, it's no standard, it's on the metal. Here, we're actually standard. So it's really one of the smallest targets, I would say, that Rust standard runs on, I would suggest. You know, you can probably get smaller, right? But it doesn't get much smaller. Oops, wrong way. Its dependencies, various Rust crypto. Crypto's everywhere in what we do. We've placed a large emphasis on security with what we do for EV chargers. In fact, what we found when it comes to the power electronics world is they tend to be good with hardware, like great with hardware, but the software always seems to be lacking, right? And we've heard these sort of stories, I think, from a few people. We use Chrono, Clap, flip-flop, mutable chunk map I wanted to specially mention. I don't know, has anyone come across a mutable chunk map? It is a map implementation with copy-on-write semantics. Really good for cloning and sharing, and I do advise you to go and look that one up. We use Siborium for binary JSON, so we don't, when we persist data, then we do so using CBOR. Anyone come across CBOR or use CBOR? Cool. Yeah, it works really well. So I'd highly recommend it. Postcard. Postcard's really cool as well, from James Munns. And what Postcard does is it's a great way of serializing structs in Rust. The serialization from structs is really quite efficient. It uses variable length integers and so forth. Streambed RS is another project that we developed. It actually comes from, we actually ultimately started, one of the founding companies of Cuprous actually was a spin out of Cisco, which started Streambed. There's a whole history there, a whole talk I could give on that one. But we originally wrote that in Scala and on the JVM and using Akka, and we've rewritten it effectively in Rust. And that's all open source, it's available. We have like a Kafka-like commit log. That, and I got these numbers yesterday. I just made doubly sure that I'm not, telling you any fibs here, but 32K. So who wants a 32K size Kafka, in their world? And we have a secret store that's based on HashiCorp Vault that, sits in 45K. Okay, and these are all single nodes for the targets. Use Tokyo, made very small contributions to Tokyo along the way, and Warp. On the front end, we use Chrono, Glue. Don't know if you've come across Glue. Glue's quite a nice little library in terms of just making some of those things in WebAssembly just a little bit easier. We use immutable chunk map again, so U. So I don't really know if there's much else that you should use right now. I think U's been great. It's worked really well. I've personally written about 5 or 6 production targeted apps now in U. And UChart, which we created and we've open sourced as well. So it gives SVG charting primitives for the use of, in conjunction with U. About 30% of our time goes back into open source. We're big believers in open source, and we're big believers in not just taking. We feel that all organizations should strive to give back if they can. That's how the whole thing. That's how the whole thing keeps running. As I said before, our entire stack is Rust. There isn't. I can't think of anything that's not Rust actually in there. For any doubters, which I'm sure is no one in this room, but Rust is so ready for prime time. I mean, it sounds obvious perhaps to most of us in here, but it is still a question that gets asked, And it's empowering, and this for me was my first firmware targeted app production, and I've been writing software for a bit, but Rust did the job, and I think fundamentally you've got to be prepared to roll up your sleeves and get in there and do things. That would be my underlying summation of where Rust is at right now. You can certainly take things off the shelf, Tokyo and Warp, and Warp can be a bit interesting. But there are libraries out there that you can actually use pretty much straight away and be productive with it very, very, very quickly. And I feel like there's been a lot of change in that direction over the last year and a half. I've personally been using Rust for 2 years. But Rust is definitely becoming, its ecosystem is definitely becoming a lot richer in that regard. So, what we're about is fundamentally about the electronics and using Rust with the target goal of using it as a language for efficiency and reliability. How did it go? Was that 10 minutes? So, questions, I suppose.
Can you repeat the questions?
I will repeat the questions, yeah. Any questions? Yes, sir.
So my background is I've done a lot of Haskell, a bit of Rust, and a bit of Scala.
Yep.
And my question is, going from Scala to Rust,
Yeah.
what were the good things out of doing that?
Yep.
And what were maybe the costs of doing it?
So what were the good things of going from Scala to Rust, and what were the costs? And what were the bad things? Okay. The good things, first of all, I think that the transition was relatively straightforward. There are a lot of things in Rust that feel familiar to the Scala developer, I would say. In particular, I mean, the type systems of both are great. I think with Scala 3, it's probably stronger in some ways, perhaps there now, but that doesn't mean that Rust is no way. I mean, it's certainly good enough. You know what I mean? What else was good about it? Yeah, so I think because of the familiarity of Scala, that certainly helped me personally sort of transition towards it. And then you get the small binary sizes and the instant startups, right? Which is it's for us in this domain that we're in as well. There's simply no choice about that. But even when you're considering running in the cloud in an enterprise-style context, then it still makes sense to have these native targets because you end up choosing the smallest machine on AWS that you can. In fact, the machines that AWS and the others offer, they're all too big. I want them even smaller, right? Okay, single core, we can't get down beyond that one very much, right? But give me something with 128 meg of RAM or something, I don't want to go the other way. Everyone's going the other way. I feel like we're actually, yeah.
I want to chime in on that. Also, having done that same transition, one thing that changes the way you think about everything is zero cost abstraction. So type class cost nothing. They're just traits, and there's no retable that compared to Haskell or
Yeah. So in terms of the bad things, I honestly mean this. There have not been any bad things. Perhaps the challenging thing. Well, you could argue that getting in there, having to roll up your sleeves and doing things yourself a little bit, right? You're definitely doing a lot more of that in this world right now, but that's a moving target. Learning about lifetimes was this really new concept, and the borrow checker doesn't seem to bother people as much as lifetimes. So I think that's probably maybe not really a downside, but it's just that you've got to spend time to sort of learn that.
Like not with the type system, from a Haskell perspective, I'm so used to pass and that don't really have nodes and Rust don't apply kind of type. So is that did that come up or in your space?
So do I miss anything about the Haskell type system, for example? Do I find and the Scala type system in Rust? No, but maybe I'm just a boring developer, right? That has probably never pushed things far as what one can push themselves in that regard. I have not found to be lacking in that. It hasn't prevented me from doing anything. In fact, what I want to say almost as well is it's kind of made imperative cool again. It's made imperative safe and easy to reason about. Whereas, of course, Scala's direction, well, not so much as as with Haskell, was the functional one because fundamentally we want to be able to reason about our programs, right? And we can still reason about our programs and be imperative. So I've not really missed anything, no.
I think we are on time. So thank you, Christopher.
Thank you.